Hello everyone, this is Professor Roman. Welcome to the 21st video in my video lecture series, An Introduction to Discrete Mathematics. In this video, we're going to continue our discussion of counting techniques by looking at the case of permutations. So let's begin with the official definition. Suppose that k and n are integers, k less than or equal to n. A word of size k with no repeated letters taken from a set of size n is called a permutation of size k taken from a set of size n. A permutation of size n taken from a set of size n is often called a permutation of the set. So here are some examples. The permutations of size 2 taken from this underlying set, A, B, C, D, are these 12 permutations, A, B, B, A, C, C, A, and so on. The permutations of size 3 taken from the set S are shown here. There are 24 of these, so I organized them by the letters that actually occur in the permutation. Since the permutations are of size 3, there will be 3 letters involved in these permutations. This group here involves the letters A, B, and C. So we have ABC, ACB, BAC, and so on. This group involves the letters A, B, and D, and so on. Now, the multiplication rule gives a simple formula for the number of permutations of a given size. But first we need a definition. This is something you may very well be familiar with, but we'll go over it anyway. The product of the first n positive integers is denoted by n with an exclamation point, and that is read n factorial. Don't know where the word factorial came from. Guess I should look it up. But in any case, this is n factorial. 1 times 2 times 3 all the way up to n. And for convenience in formulas, 0 factorial is defined to be 1. It doesn't fit this pattern, but it's defined to be 1. Now, more generally, this is something you may not have seen. If n and k are integers in this range, then this symbol, which is n in parentheses and a subscript k, is defined to be n times n minus 1 down to n minus k plus 1. Okay? Where again, for convenience in formulas, when k is 0, it wouldn't make any sense here because you'd have n plus 1, but these numbers are supposed to be descending. So we just define that to be 1. This number is called a lower factorial or a falling factorial. So I would read this as n lower factorial k. And you'll see in a minute or two why anyone would bother with this concept. The ordinary factorials are special cases of lower factorials. N factorial is n lower factorial n, because if you stick an n in here for k, this will be the product n all the way down to 1, and that's n factorial. The factorials grow quite quickly, so by the time you get to 10 factorial, you're in the 3.5 million range. It does take a bit of practice to get comfortable manipulating lower factorials. The first thing to notice, and perhaps I should have said this earlier, but n lower factorial k is the product of exactly k factors. They're consecutive factors, each one less than the previous one, n minus 1 down to n minus k plus 1. There are k factors here. And you might be confused, why is this k plus 1 here? Why isn't it just n minus k? Well, if you rewrite this n lower factorial k, replace n by n minus 0, then you have n minus 1 and so on. If you want k factors, because you're counting from 0, the last integer you subtract will be k minus 1. And n minus the quantity k minus 1, of course, is n minus k plus 1. Okay? So if that went by too fast, you should pause and go over it again. It's not very deep. But it's important not to make the mistake that I see students make quite a lot, and that is to think that this is correct. Okay? It's n minus k plus 1. Lower factorials can be expressed in terms of ordinary factorials because n lower factorial k is this number by definition, which is n factorial divided by n minus k factorial. And this is one reason why defining n lower factorial 0 as 1 is convenient, because when k is 0 here, then you'll get n factorial over n factorial, which is 1. So this definition is made, in a sense, to fit this formula that n lower factorial k is n factorial over n minus k factorial, even when k is 0. This side makes sense, of course. When k is 0, it doesn't require a definition. Now, as far as computing lower factorials by hand, calculators will do it, at least most calculators. It's generally easiest, at least for small values of k, to use the fact that there are k factors. Starting with n, reducing by 1, do it k times. That's the way I think of it when I have to compute, let's say, something like 1,000 lower factorial 4. I don't do that very often, but if you're calculating poker odds, the lower factorials come up. So anyway, the way I would think of this, as soon as I see this, I would think, okay, this is 1,000 times 999 times 998, 4 of those factors. So I could write this immediately. Then a calculator will handle this. This formula is not very practical. It's a great choice for theoretical issues like manipulating factorials, which you'll do in the exercises. But it's pretty much lousy for using a calculator. In the same example, 1,000 lower factorial 4 is 1,000 factorial over 996 factorial. A calculator couldn't touch these factorials. They're way too big. They'll overflow the calculator. So this is not a useful formula for computation. Well, now that we have that taken care of, we can go back to the counting of permutations. And here's the theorem. The number of permutations of size k taken from a set S of size n is denoted by p n comma k. This is common notation. And it is equal to the lower factorial, n lower factorial k. So here is the formula in all its glory. When k equals n, we have the permutations of the set S, and that is Pnn, which is n factorial. So the permutations, the number of permutations of a set of size n is n factorial. The number of permutations of size k from a set of size n is the lower factorial, n lower factorial k. By the time we get finished with all the counting techniques, you'll be very happy to see these formulas because they're by far the simplest ones. So you might want to take a little time to absorb this. Make sure you're good with this before we go on. I think that's good advice for this entire period of time when we're discussing counting techniques, because they get progressively more involved, and it's easy to get lost or confused if you don't keep up with the earlier stuff. The total number of permutations of all sizes, from size 0 to size n, taken from a set of size n, is this sum of all of the lower factorials. And that's about the best you can do. There's no simple closed formula for this sum, at least as far as I know. As to the proof, it's pretty straightforward because it's the multiplication rule. Constructing a permutation of size k from a set of size n can be done by performing k tasks. The first task is to choose the first letter for the permutation, and that can be done in n ways. The second task is to choose the second letter for the permutation. By letter, I mean element, And that can be done in n-1 ways because we can't repeat. We can't use the letter we've already chosen in for the first position. And as we work our way down, the kth task would be to choose the letter for the kth position. But by that time, we've already chosen k-1 letters, so we can't use those, so we're left with n minus k plus 1. And so the multiplication rule, checking the independence, it's okay. Multiplication rule gives us this product, which is exactly n lower factorial k. And this is why the lower factorials are so important. They count permutations. So, as a simple example, in the first lecture on counting techniques, we had example 192. How many ways are there to order 9 books on a bookshelf? It's 9 factorial. 362,880. So, if you have it in mind to rearrange the books on your bookshelf in a different order each day, it would take you just a little over 994 years. So maybe that's not such a good idea. Now there is a point of potential confusion. I've seen this in many places, not just among my students, but in other books all over the place. And I want to clarify this for us. I'm not criticizing any other authors. Every author has to make their own decision here, but this is my decision, and I think this is the one that makes the most sense. So to be absolutely clear, this symbol, PNK, is defined as the number of permutations of size k taken from a set of size n. End of story. It's not defined to be n lower factorial k. It would be sort of a waste, a duplicate of notation to simply say, let's set this expression equal to this expression. And similarly, n lower factorial k is defined to be this product. It has nothing to do with permutations on the surface. Initially, it's just defined to be a product. It's not defined to be the number of permutations of size k taken from a set of size n. Finally, it's a theorem in combinatorics that this value is equal to this value. Okay, so I urge you to think of things this way. It's neat, it's clean, it's clear. Unfortunately, not all authors adhere to this interpretation of P and K. Sometimes you will find an author who says P and K is defined to be n factorial over n minus k factorial. Okay. It may be that these authors don't care to define the concept of a lower factorial, so that would be one way out, but I don't think it's good pedagogy. Now let's take a look at some problems we can solve using this theorem on the value of P and K. Suppose we wish to arrange 6 different math books, 4 different computer science books, and 3 different chemistry books on a single bookshelf. I will apologize now for a bunch of examples involving arranging books. As I said before, I'm trying to keep these examples simple by removing irrelevant data. Maybe this is the kind of problem that will come up in physics regarding electrons around an atom or something else, but it doesn't seem important to go into any physics here when we're trying to understand the underlying mathematics. And so if you will trust me, to the extent that these counting techniques are important in mathematics and in the sciences, then we can just, deal with the simplicity of books on a bookshelf. So, how many ways can this be done? In how many ways can this be done if the math books must come first, which is only right, of course, then the computer science books, and finally the chemistry books? In how many ways can this be done if books of the same subject must be kept together? Okay, so as to the first part, how many ways can you arrange all these books on a bookshelf essentially without regard to the subject? Well, you got 13 books, so each ordered arrangement is a permutation, and there are 13 factorial of those. So you have 6,227,020,800 ways to arrange 13 books on a bookshelf. Okay. As to part B, now we want the math books to come first, then the computer science books, and finally the chemistry books. Well, there are 6 factorial ways to arrange the math books on the bookshelf, because there are 6 math books. There are 4 factorial ways to arrange the computer science books, and 3 factorial ways to arrange the chemistry books. We have to perform each of these tasks. We'll put the math books on the shelf first, then the computer science books, then the chemistry books. The independence rule holds, so the multiplication rule applies. 6 factorial times 4 factorial times 3 factorial. 103,680 arrangements of the books where the math books rightly come first, and then the computer science, then chemistry. I don't mean to slight chemistry. I like chemistry a lot. Okay, part C. In how many ways can this be done if books of the same subject must be kept together? We always look initially for the task arrangement because then we can use the multiplication rule. So think of it this way. The first task is to choose the order of the three subjects, math, computer science, and chemistry. Once that order is chosen, the problem reduces essentially to part B, with possibly and generally a different order of the three subjects. Fix the order of the subjects, then you will get these three numbers, and they may be, you'll take the product of these three possibly in a different order, but what's the difference? Multiplication is commutative. So the first task, choose the order of the subjects. There are 3 factorial ways to do that. Once that's taken care of, the second task would be to arrange whichever subject came first, those books, on the shelf, then arrange whichever subject books came in the second on the shelf, and finally the third group. So it's going to be 6 factorial times 4 factorial times 3 factorial, or some rearrangement of this product. So the total will be the 3 factorial times this set of factorials, and you'll get 622,080. Now, I don't mean to be pushy about all this, but I think if you just think about this problem for a minute and ask yourself how you would handle this problem, how you would solve this before you started this course, or backing up to before you knew about factorials. How would you ever figure out that arranging 13 books can be done in 6,227,020,800 different ways? I don't have a clue. You're certainly not going to actually do the arrangements and count how many there were. Nobody has that kind of lifespan, and it'd be a total waste of time anyway. But I think this example, if you'll overlook the fact that it's kind of silly in a way, shows the power of counting techniques, and we have just begun our study of counting techniques. Okay. So that's just my 2 cents. Next example. This is a much simpler one. In order to send messages from one ship at sea to another, flags called signal flags are sometimes used. You can see this in the movies where they run up these little triangular flags on a flagpole. I think usually there's 3 of them. If a certain ship has 10 signal flags and 1 flagpole, and if each ordered arrangement of 3 flags is a different message, which it's bound to be, the number of messages possible is P10(3), which is 10 lower factorial 3, which is 720. Suppose that a certain state has license plates consisting of 3 letters followed by 3 digits. We talked about this before. In California, this was the case. The number of license plates that do not have repeated letters or digits. For the letters, you have P26, 3 possibilities. For the digits, you have P10, 3 possibilities. So you have the 2 lower factorials, P lower factorial, 26 lower factorial 3, 10 lower factorial 3, 11,232,000. Now, before reading on, I'll cheat here. Do you think that this is a relatively small or relatively large percentage of all the possible license plates where you can allow repetitions. These are the ones with no repetitions. Is that 10%, 20%, 30%, 80%, 90% of all license plates? Well, we have the techniques for determining. The number of all possible license plates, we saw this before, 26 cubed times 10 cubed, 17,576,000. So the percentage with no repetitions is this number divided by this number. 64% of all license plates have no repeated digits or symbols, no repeated symbols, letters, or digits, which means about a third of all license plates have a repeated letter or digit. So next time you're driving down the freeway, you could glance at license plates. A third of them will have a repetition in either the letters or the digits. So this is another example of the power of counting techniques. Okay. The next example has a little different twist, but it's an important one, and it's one that comes up a lot. What is the number of ways to order 9 books on a shelf if book B2, I didn't want to make up titles because that's, again, irrelevant information. If book B2 cannot immediately follow book B1, they must be separated by at least one book, or B1 could come before B2. Okay. But B2 cannot immediately follow B2 cannot immediately follow B1. So B2 could come before B1 or much later than B1. Now this is, I kind of stumbled over explaining it. This is a little bit complicated. In a simple way, it's complicated. It's an example of the type of question where it's easier to count what you don't want and subtract that from the total. So in particular, we count the number of permutations of size 9 where B2 does immediately follow B1 and subtract that from the total, which is 9 factorial. That's all arrangements of the 9 books. Now, a permutation of the 9 symbols, B1 through B9, in which B2 does immediately follow B1, is essentially just a permutation of 8 symbols. If you glue B1, B2 together like this and treat it as a single symbol, you have 8 symbols, and there are 8 factorial permutations of these symbols. So the answer to this problem is the total number of permutations, 9 factorial, minus the 8 factorial permutations we don't want. And when you do the calculations here, you get 322,560. So this is much easier than trying to compute directly the number of ways to order 9 books if B2 can't immediately follow B1. The situation where it's easier to count what you don't want and subtract from the total is fairly common. And so whenever you're faced with a counting problem to solve, it's not a bad idea just to take a moment to think about whether it might be easier to count what you don't want. Now, of course, you still have to be able to count the total, but as I say, that sometimes is the way to go. Next example, how many bytes, these are binary words of length 8, are there that contain at least 2 ones? Again, rather than try to count this directly, it's easier to count the number of bytes that do not contain at least 2 ones and subtract those from the total. The total is 2 to the 8th, or 256 binary words of length 8. And that comes from the multiplication rule. Now, a byte that doesn't contain at least 2 ones either has no ones or exactly 1 1. There's only one byte with no ones. All 8 bits are zeros. And there are 8 bytes with exactly 1 1, because there are 8 positions that you can place the 1. The rest gets filled with zeros. So the answer to this question is 2 to the 8th minus 1 minus 8, or 247. And the hint here is when you see words like at least, and what follows is a small number, at least 1, at least 2, at least 3, it's probably better to try to count what you don't want, because that's at most 1 or at most 2 or most 3, and those numbers are generally easier to count. Okay. Permutations of objects are ordered arrangements of those objects, but they're linear arrangements. They're arrangements in a line. Now, you could bend that line a little bit, but it's basically a linear arrangement. On the other hand, a circular permutation of n objects is an arrangement of the objects in a circle, a closed circle. And that means there's no first element and there's no last element, so it changes the counting. Here is a picture. There are 2 circular permutations of the numbers A1 through A5. So I have A1, A2, A3, A4, A5. Here I have A4, A5, A1, A2, A3. Okay. Now, circular permutations are considered to be the same if one of those permutations can be rotated to be the other. And that's the case for these two. Listen to the indices as I go clockwise. 1, 2, 3, 4, 5. And then if I come down here, 1, 2, 3, 4, 5. These are the same circular permutation. The problem is then to count the number of distinct circular permutations of n objects. Now, the simplest way to do this is to select one of the objects, say A1, and place it at the top of the circle. Fix it at the top of the circle. Then you can place the remaining n-1 objects in any order you want around the circle, starting at the position immediately clockwise to the top, A1. So what you're doing really is pinning one object at the top. You can pin it anywhere, it doesn't matter, so that no rotations can occur. Well, the remaining n-1 objects can be placed on the circle in n-1 factorial ways. That now is essentially a linear permutation. Okay. So the number of circular permutations of size n is n-1 factorial. And here's an example. Okay, that concludes our discussion of permutations, although all this material will come up many times in the future. So thank you for watching the video, and I hope to see you in the next video.